Welcome back to yet another edition of Pre-Press at Fullerton College with Professor Ben Hewitt, and we're still going through the PIA's Pre-Press Training Handbook, Section 4.3, Digital Image Basics, although some of the information here may be fundamental, but I wouldn't call it basic. So, we were talking last time about the Nyquist theorem and how, long story short, you need 300 dots per inch linear, don't worry, it's not an area calculation, 300 dots per inch resolution at the size that you want to print cleanly on a good quality press. Although we also know that there's a lot more math and a lot more details depending on exactly what line screen you're using, which will depend on the paper and the ink. But for standard commercial printing, 300 DPI, dots per inch, or PPI, pixels per inch, same thing, is what you're looking for. Now, a lot of times you're going to be getting images from somebody else. So we have to take the files that somebody else gives us and check them to make sure they're going to be the proper resolution. Make sure that they're going to have double the dots per inch that the lines per inch the press is going to use. You want 2 dots per line. Basically, 2 pixels makes 1 halftone dot. Again, that's part of the, let's just scroll up to it. The theorem, a few slides up from where we were here, LPI times 2 times the percent. So you need double. So that's the resolution. There's also the video I put up where you can, how to do this in Photoshop, how to quickly check the image size is under image size. And here it is also in this slide, is a picture of that. And if, as long as you have resample, which they have checked down here, unchecked, you're able to go ahead and test based off of what this has to see what resolution it will be. And I'll do the math for you. After all, that's what computers are invented to do. Now, the 300 dots per inch works for photographs, for JPEGs, PNGs, PNGs, TIFF files if you are so lucky. But if you're not using a photograph, if it's not a continuous tone image, if it's line art, if it's an illustration that was drawn pen and ink and then scanned or photographed, you actually need a lot more. To get this to look good in digital printing, those need to be 600 dots per inch. And if you're going for offset printing, you want 1200 to 3600. Sorry, that is actually the resolution of those plates. You need 1200 dots per inch, because when you're using a photograph and there's all those different tones in the picture, that mosaic of those different colors and different tonal ranges helps camouflage the fact that the edge is made up out of squares. When you're just using a stark black line on a white background, or vice versa, there's nothing to hide your edge. Your edge is on full display for everyone to see. So you need to make those pixels a lot smaller so that the viewer doesn't see the pixels, but sees the line they make. So you need to have 1200 dots per inch or more for line art. That is, if your line art's not already vector. And these days, a lot of it is vector. So it's a little bit less of an issue at that point. And in which case, if it is vector, it's just going to come at whatever the maximum output was for the device out doing the output, because that's how vector works. Okay. So we're going to talk about the actual memory that these take up, the storage size of these files. Now, the thing is, you can kind of eyeball them and sort of know if it's going to work or not. I mean, you can really only eyeball it in the negative, not for the positive. You can eyeball a photo someone sent you. If it's like 200 kilobytes, it's probably not going to be big enough to print. If it's a couple megabytes, it probably is going to be okay, but still might not be, depending on how the memory was used. I don't like using file size to determine printability. I always open my images and check them in Photoshop, because there are too many variables at play to be able to definitively say that this number of megabytes is going to work, because the number of channels being used, the number of pixels per channel, and the number of bits used to specify the gray value of each pixel is what really matters in determining file size, not just the number of pixels. So if you have a huge image that's only grayscale, it may not be that large memory-wise. And if you have a relatively small image with very complicated color settings, very, very, very detailed, accurate color, putting a lot of memory per pixel. Even without that many pixels, the image size or the file size is going to be huge. So again, I don't like using this one. It's not an accurate gauge, and it's not a good way to judge. So let's talk about file formats. You know, if you're working in Photoshop or you're taking photos on a camera or scanning, you don't really have to decide your file type until it's ready to save. Now, the file format tells you how is the computer remembering this image. Each one of these things, JPEGs, Photoshops, PDFs, TIFFs, BMPs, those all have their own way of remembering what the image is, and how they remember it does matter, because it's not just, an image is not just an image. An image is also the way the image is remembered. Here are three common ones, although one of these things is not that common anymore. TIFFs, EPSs, and JPEGs is. Yeah, I did that on purpose. And JPEGs. These are three common image files. PDF is kind of an image, but not really an image. It contains images, but it is not itself an image. So let's talk about these things. The tagged image file format, the TIFF. This was, as digital photography was taking off, and as desktop publishing, now known as graphic design on computers, was taking off, Apple and Microsoft were going neck and neck to create the perfect file, TM, for saving and reproducing images. I believe the Microsoft version was a picked file. I might be wrong off the top of my head. The Apple version was the TIFF, the tagged image file format. And the TIFF is a very high quality picture. It did actually kind of win that competition for what was left of that competition, because as we'll get to, the competition for making the highest quality image was undercut by another idea that came out and kind of supplanted it. So anyways, much like some video recording equipment that was going to be the thing and then wasn't the thing. Again, we'll get there when we talk about the one that actually won the competition. So the TIFF can be used on Mac and Windows nowadays. It can be used in all desktop publishing applications and programs. The file size is moderate to big if you don't compress it, and it supports clipping paths. So you can have transparency in it and not the whole image covered, no white background. It uses something called LZW compression, which we'll talk about, to make the file a little bit smaller. EPS is the largest file type you can have for a photo, unless you have a very complicated Photoshop RAW file or something. But EPS was the most common one for a while, although it's not as necessary anymore. EPS can have a very high quality picture in it if it's placed in at the right size, and it can be placed and used in all desktop publishing programs. The file size is going to be much larger because it really is two pictures in an EPS. The EPS saves the actual image file, and it also saves a low resolution preview file to show you what it looks like on the computer. Because in the older versions, you weren't able to look, and the computers weren't robust enough to be able to preview an EPS file and translate it back into computer code. Because they're not going to tell you this right here, but Postscript, that is the stuff that is being encapsulated, is not computer language. It is printer/plate maker language. So instead of showing you how your Apple or your IBM, oh wow, I'm old, your Mac or your Windows computer is thinking, it's actually translating how your printer wants to think. It's not speaking Macintosh or Windows, or even Linux. It's speaking HP or Xerox. Anyways, so Postscript is the thinking language that digital printers and digital plate makers think in. So encapsulated Postscript is saving basically a print file and then translating it back to you on your computer screen. So it wasn't able to do that all in one go. It does a few things, and they're still necessary for these, that other things don't do very well. Clipping paths is always important if you don't want to have that white background on a traced image, but it also has duotone, which we talked about a few videos ago. Not many things support duotone. So if you need a duotone, and it's rare that you do, you probably need to use EPS to save it. All right, we're going to talk about different types of image compression now. The two main types out there are LZW and JPEG compression. People confuse them because they hear compression and they assume it's JPEG, but they only do one thing the same way, which is they both make your files smaller for easier saving and easier transfer. But how they do that and what they do is a huge difference. LZW is known as lossless compression, and it does not change the quality of the image. It simply organizes the memory of saving that image better so that it can be remembered on the computer later without having to remember the whole thing. JPEG is lossy compression, and it loses some things. Let me switch over so I can show you an image I made. Here's a bit of a silly picture my wife helped me make today. Thank you, Lonnie. So here's me packing a suitcase to go somewhere. Where? I don't know these days, but here's me packing a suitcase to go somewhere. Lossless, or LZW compression on the left there, is like folding your clothes neatly into a bundle to make them fit better into the suitcase. If you just try to mash them in, they're not going to fit. If you fold them nicely and you tuck all the things inside each other, your shirts can even stay ironed and come out looking smooth if you bundle them properly inside your trousers. But lossy compression is like the image on the right. Lossy compression says, shove everything in there, and if it doesn't fit, cut it off. Of course, it's done more detailed than that, as you'll see in the JPEGery video. So LZW creates a lookup table, and it basically looks for the different colors being used in the image. And the more the colors repeat, the less it has to remember. It kind of creates itself if any of you know these things, a paint by number. So here's a good example down below using text. I am very happy to be in the printing industry. I love printing. Printing is very interesting, and the printing industry is always changing. Now, if you assign a number to each one of those words, and you kind of pretend they're all different colors and values of pixel. And vary is number one in our little lookup table. The is a common word, so that's number 2. Printing is number 3, and industry is number 4. So I am happy to be in the 2, 3, 4. I love 3. 3 is one interesting, and 2, 3, 4 is always changing. Same thing if you use the lookup table. So that way it only has to remember the actual color values or the actual individual pixels once if they repeat. And when they come back in, it just has to show them again. Of course, this means you're only going to be able to reduce your file size based on how much repetition you have of individual tonal colors. So LZW compression, as you can see in the image here, takes a pretty large image of about 30 megabytes down to about 20. Yes, I'm rounding. But anyways, it depends on the image content. LZW can do a really good job, or it can do an okay job. If it's all sorts of rainbow random colors, you're not going to get it as small because the lookup table is going to be basically the whole image anyways. Lossy compression has some problems. JPEG is lossy. And you'll see this in shadow areas, but over the whole thing. JPEG compression removes some of the image to make it smaller. It removes it in ways that you wouldn't necessarily notice. And again, like in the other video, basically what it's trying to do is kind of give you averages in a way that's somewhat reminiscent or rhyming, if you want to be George Lucas about it. It rhymes with the way the rosette works for halftones in printing, which is it finds a way of reminding you of what you're looking at while not showing you everything and not being totally disruptive. It makes a larger tile of 16 pixels, and it gives you the average color from within those and kind of averages and randomizes them rather than remembering every individual pixel. Because a TIFF remembers each individual pixel as its own thing, but a JPEG remembers, this part of the picture is mostly brown, so here's mostly brown. So it doesn't actually remember all of the details. So the results, though, will also vary depending on how aggressive you're going to allow the compression to be. If you use minimum compression, which is to say maximum quality, it's still going to be a lot smaller. You can see that the same image here that would have been almost 30 megabytes as a TIFF is only 3 megabytes as a high quality JPEG, and only 800 kilobytes as a low quality JPEG. So more compression is smaller, worse quality. Less compression is larger, better quality. So the more you compress it, the more pieces you have to cut off. I should probably end this video on that other image again. So here we are. Remember, JPEGs make it smaller, but they make it smaller at a cost of being usable later. You can lose a lot of important details to compression issues and compression artifacts, which we'll talk about another time a little bit more in detail. Thanks for listening. I hope you guys have enjoyed this, and Thanks for letting me be your meme.